Tableau 8, Part 2, Additivity, the Theorem of Total Probability. In our previous Tableau, we built in a formal edifice in folding inside information into a chance process, and this led to a formal definition of the notion of conditional probability. When allied with the axiom of additivity, this gives rise to a very potent and powerful principle which sometimes goes by the name of the theorem of total probability. Let us begin by recapitulating the key idea that was encapsulated in the notion of conditional probability. To begin, there is a target event, H, of interest to us, represented abstractly in a Venn diagram by that egg in your figure. Side information is encapsulated via the specification of an ancillary event, A, of positive probability. The conditional probability that H occurs, given that A has occurred, is then defined to be the ratio of the probability of the intersection of H with A to the probability of A. In words, this is the proportionate part of H that lies in A. If we clear the denominator by multiplying both sides by the probability of A, then we get an equivalent formulation which is equally evocative. The probability of the conjunction or the intersection of the two events H and A is given by a product of probabilities, a conditional probability of H given A and the probability of A. Conditioning provides us, in this perspective, a way of chaining or building up conjunction probabilities systematically via the conditioning process. Which viewpoint is better? Well, it depends upon the circumstance. In the elementary settings we've seen so far, we begin by characterizing a chance experiment by specifying the sample space, the space of possible idealized outcomes, the events of interest to us, the subsets of interest to us in that space, and finally a probability measure, which in finite settings or in countable settings we specify by specifying the mass function of atomic probabilities. Now, once a probability measure is specified, then one can go ahead and, using axioms of additivity, compute probabilities of events directly. So in such settings, it might be easier to directly compute a conjunction probability. In other settings, however, the probability measure is not specified explicitly, but implicitly. And in such settings, it turns out that conditional arguments are much easier to digest and compute. And then we think of conditional probabilities as an avenue towards conjunction probabilities. The perspective depends upon the particular problem at hand. Now, let us take the second of the two equations defining conditional probability as a starting point and see how, by folding in additivity into the process, a very rich and subtle principle emerges. So, once again, we have a target event H, side information encapsulated in an event of positive probability A. Now, of course, the picture is evocative. A is captured by the green shaded region on the left of your figure. But of course, the moment you specify A, then there are sample points left out of A. This collection comprises the complement of A. And together, A and A complement partition the entire space of possibilities. Either an outcome is in A or it is not in A. Since A and A complement partition the entire space, A fortiori, for an even stronger reason, they also partition H into two parts. And we can write this down formally using intersections as follows. H can be decomposed into two disjoint pieces. That portion of H that is common to A, H intersection A, and that portion of H which is outside A, that portion of H which is common to A complement. The union of these two pieces then comprises all of H. The whole is equal to the sum of the disjoint parts. Now this perspective is alluring because now we have managed to decompose H into disjoint pieces, and additivity of probability measure promptly rushes to the fore. The probability of H then can be written as the sum of the probabilities of the disjoint parts, the probability of H intersection A together with the probability of H intersection the complement of A. So far so good. But we now have a process of representing conjunction probabilities by chaining with conditional probabilities. We replace the first conjunction probability by a conditional probability times the probability of A, but we can replace the second conjunction probability likewise, where now A complement stands in the role of A. And now we've got a chained equation. Look at it. Absorb it. This simple structure carries subtlety and nuance far beyond its apparently simple main. The value of such a decomposition arises if, in an experiment, one can find a suitable decomposition of the underlying space. And I shall promptly illustrate this for you with a couple of examples. We should begin, of course, with something simple. And so we'll go back to one of our old regulars. We'll go back to a game of dice. And we'll build on this to build intuition, an understanding of how an identity like this can prove to be profitable, and build upon this with a second example of some subtlety, some nuance, and some importance.